Good afternoon, everyone. I welcome you at the second half of last day of Data Science School at Kiev Academic University. Next talk will be from Professor Nitesh Chawla from Notre Dame University. He works at Computer Science and Engineering department, as far as I know. He's also a fellow of Association of the Advancement of Artificial Intelligence, fellow of Association of Computing Machinery, and fellow of Institute of Electrical and Electronics Engineers. I know personally Nitesh mostly from large language models direction of research and natural processing languages in overall. Today, Nitesh will talk about generative AI with graphs, but yeah, so what's to you, Nitesh? Thank you very much for joining.
Hey, thank you again, and good afternoon, everyone. And thank you for Vladimir inviting me to be part of this school of workshops or conference that you're conducting. And it's a pleasure to speak to all of you here today. As we go along, feel free to ask questions as I present, or feel free to save your questions till the end, whatever way the audience prefers. I'm comfortable with it. So I'm going to talk today about is how do we do generative AI with specific focus on graph learning, and how do we frame the applications from a respect to sciences. So the work that I would largely be talking today comes from efforts of a variety of students and postdoc scholars who have been part of my lab. So on the top row is the current group of PhD students, and in the bottom row and on the next slide are the graduated PhD students or the postdoc scholars who have been through my research lab. So this really is, sort of an accumulation of different threads of work, ideas, contributions made by a variety of the students, postdocs that have been through my lab. So why graphs, right? So graphs essentially are ubiquitous. If you think about in social media, whether it's looking at LinkedIn, Twitter, now there's no Twitter, X, Snapchat, Instagram, or are you looking at finance, e-commerce networks, or financial transactions, or shopping online places, whether it's Amazon or eBay. And more recently, graphs have the molecular structures that are often found in chemistry have been represented as graphs as well. So we could take any complex system. I think of social media or the financial system, the e-commerce system, or even the chemical system is a complex system. These complex systems have different components in it. Those components could be individuals, people. These components could be organizations doing transactions, buyers, sellers. These components could be atoms that are connected by chemical bonds, which are the edges of that network. So we could create a graph-like abstraction from this data. And what a graph-like abstraction from this data gives us this graph representation or network representation from the data or the complex system allows us to capture interactions, allows us to figure out what may be some of the higher order patterns of information exchange or influence or chemical interactions, etc., that are apparent in this data. Now, of course, in the chemistry example, we have a molecular structure which looks like this. So it comes in as a graph, although I should mention that the molecular structure is also three-dimensional because it has orbital and other information that sort of captures where it's in space, etc. So when we first started with this work, this was about, as I said, historically, I was more in the learning from imbalanced data domain, which we still do quite extensively in the lab. But about a decade or so ago, about 15 years ago, we sort of started thinking about graphs and networks and how we can develop machine learning algorithms to tackle challenges apparent in these graphs. And how do we sort of featureize these graphs or these networks? And this was pre-representation learning days. This was pre-Word2Vec, pre-everything else that we are seeing today. So it was still a lot of manual engineering. So we would get an input graph or an input network, and we would do some feature engineering and whether we would compute some node level features, graph level features, edge level features, etc. Think of them as structured features or feature vectors, and then deploy or develop a learning algorithm for a particular downstream task. So we did a variety of work here in whether we think about community detection, link prediction, not just if a link will form, when a link will form, etc. So we focused quite a bit on this sort of a journey of how do we efficiently feature engineer, extract what we can from a graph, build a feature vector, then optimize the learning algorithm for a particular task. And then we also discovered, as we were working on this area, we also realized that there are these higher order dependencies of in a graph or a network wherein nodes multiple hops away may influence a node. So there are these dependencies that may happen in a complex network or a graph, which may affect its overall performance, so that the graph and then is not truly representing the underlying behavior for complex system. What I mean by that is generally when we create these networks or graphs, I'm going to use networks and graphs interchangeably throughout the presentation. So please bear with me on that. So as we think about building these networks, the assumption that we often make is there's a Markovian assumption, first order Markovian assumption, that there is A to B has an influence, B to C has an influence, C to D has an influence if A, B, C, D are nodes. But what we don't quite capture is what if something happened at A that led to B, and because A and B happened that led to E instead of C, and then A, B, and E happened that led to F instead of D. So, which means that there's this memory in these complex systems that happen through an interaction. So that's what is a higher order network. So how do we represent these higher order dependencies in these networks or graph? Which truly capture the behavior of a complex system. So that was the work that we also did in higher order dependencies in networks. So all of these works have been extremely well accepted, etc., in the community. But then in about 2016, 17, there was this surge of interest, Word2Vec had happened, and there was a surge of interest of, can we represent graphs leveraging, say, a Word2Vec kind of an encoding embedding method to do representation learning on graphs. So there was some initial work that came out in 2016, 2015, wherein for homogeneous graphs, so imagine if the graphs are essentially like a sentence, a language that's being represented by a graph. I could then flatten it out and say, okay, the nodes that are connected to each other are like words that occur in a sentence together as part of a language representation. I can now apply similar concepts as a Word2Vec and do representation learning on these graphs, which will then give me an embedding or a feature representation. The beauty of this work was that we don't have to manually compute structured features as we show in the top figure. Instead, we could simply do a graph, give it to a neural network, do representation learning, get the embedding layer, and then we just use it for all aspects of any downstream machine learning task. The assumption being that the embedding vector representation or the feature representation that we derive from the embedding is a generalized representation of how that graph is behaving. So that's what sort of we somehow captured here. So then, as we were looking at, the initial works that were Node2Vec, etc., that were produced focused on homogeneous graphs. What that means is these graphs have singular type of nodes, singular type of edges. There is no heterogeneity. There is no typed edges or nodes, that the nodes are of different types, different classes, edges are of different types, etc. So there was no such attribution available for edges and nodes in those works. However, if we look at this graph on the very top left, we basically can see here that a graph could be, and largely graphs or networks come as heterogeneous representations where within a graph, it's the author or the citation graph or the publication graph. The author, the node could be the organization an author belongs to, whether that organization is a university. A node could be the author, who is the author. A node could be a paper, the paper the author writes. The node could be a venue, where was that paper published? So essentially, if you look at this graph structure on the top left, what we are seeing is there are different types of nodes. But then as well as there are different types of relationships. The authors are connected because they work at the same organization. The authors are connected because they collaborate. The authors are connected because they wrote that paper. The papers are connected because they cited each other. The paper and the venues are connected because the paper was published at a particular venue. So you could imagine a graph that says, oh, I have a node of a type author, and that author works at this organization. This author published this paper. This author collaborated with the other authors. This paper cited other papers, and this paper was actually published in this conference. So there are these variety of dependencies or edges that occur in these networks. So then we said, all right, so this is a heterogeneous structure. This is not homogeneous structure. So there was this beautiful work on metapaths that had been done. She said, could we sort of prescribe metapaths? So typically, the way Node2Vec and other homogeneous network embedding methods have worked is, it's a random walk-based instantiation. You take random walks across the graph and you follow the nodes, and you basically, based on the random walk, you could say, hey, I will now contribute to the embedding layer. Instead, we said, what if we prescribe a particular path or set of paths that the walker may take? We can say, all right, the walker should only take author, paper, author path. So the walker will not take any other path, and we are forcing the author to the walker to go through those things. Or we could say that the random walker should take author, paper, venue, paper, author path. So that's the path that it takes. Or we could say that it takes organization, author, paper, venue, paper, organization path. So you're constraining, and what you're saying is, hey, Mr. Random Walker, walk this path based on the prescription or the schema that I'm giving you. And we can prescribe multitude of such metapaths. So then now we have sort of created, if you will, an input layer based on this notion of this walking. And now we can do similar kind of embedding in learning to develop the features. And then something else that we developed as part of this work was the skipgram method that was used to compute the probabilities at the end. We converted that into heterogeneous skipgram where we computed them. What's the probability of a venue based on the venue nodes, probabilities of authors based on author nodes, probability of paper based on paper nodes, not across all the nodes that a skipgram may do. And there were other things that we did along the way in terms of what we did as a loss function, etc. So this became the first method for representation learning for heterogeneous graphs. This is what we published in 2017 and has really set the field in many ways. So this was my student Yu Zhao Dong who did this work. Because of this work, he was also recognized as a runner-up Best Dissertation Award at KDD, Rising Star Award at KDD, and he's now a professor at Tsinghua University. So this was, but then as we looked at it, we hadn't quite solved the heterogeneity of graph problem, because what we had tackled is how do we deal with the heterogeneous structure, nodes, edges, etc. We didn't quite deal with the content. So if you look at the bottom layer, in that bottom layer, you would see that there are users. The users have items, and the items could have images, could have description, could have attributes, whether movies or books or products, etc. Or even if we look at the paper collaboration network, the papers have content, images, etc. So how do we sort of capture all of this information that is rich information within a graph, which is beyond the structure, but is truly representing the function of behavior of a complex network? So the graph neural networks had been popularized, but again, they were also mostly working on homogeneous graphs. So we developed a heterogeneous graph neural network work back in 2019 that essentially addressed complexity of a graph such that it can capture a variety of data, not just structure. So we could get uh, different content. We could build different sort of, encoding layers and do aggregation later. And at the end, do an attention network and compute an overall graph context loss, and then give you a final embedding. Because at the end of the day, what we are trying to do is, can we capture all this information that exists in this rich graph or a network representation of a complex system and get it to an embedding stage, a feature vector that a machine learning algorithm can learn from. Because that's what the machine learning algorithm is saying, is give me a feature vector. So it's not how do we create that feature vector representation or the embedding layer that the learning algorithms could then be used for different downstream tasks. Of course, we're using a learning algorithm to create that representation layer, that's a given. But then in the end, for downstream tasks, what kind of feature vector we can give so they generalize. So as we have been thinking in the last few years, since we have done this work, we have had a variety of papers on generative AI, etc., or graph learning, learning on graphs, from few-shot learning to mass autoencoders to link prediction works, etc. So a rich body of work has come out of the lab. However, as we go beyond this framing, we think about data-centric machine learning or model-centric machine learning. There is an area that we have been quite focused on, whether it's knowledge, whether we call it knowledge-centric or knowledge augmented, etc. How do we enhance the performance of these models such that they can, using external knowledge, or can we distill knowledge from a large model to do a smaller model at the end of the day? So I'll give you some examples. Right? One framing of this language models is that one could have a lot of data. The data, there's a cost of annotating data. If you think about vast majority of data from real world applications, it is collected without significant annotation or labeling. The cost of annotation or labeling is expensive. So we may recruit experts, or we may recruit a wisdom of crowd to get the labels annotation in, and those labels and annotation may not be perfect, but we may have to go through an iterative process of doing so. So but that annotation or labels is in many ways representing the knowledge of the experts, knowledge of the wisdom of crowd, if you will. And then the machine, then it becomes a labeled super task that can be fed to a supervised learning problem for doing certain predictions, doing certain inferences. Now, can we eliminate the human in the loop? Can we do more of a self-supervised learning framework such that the labels or the annotations are derived by a machine learning algorithm itself? So then the machine learning, the labels or the annotations in many ways are knowledge, because if we're relying on a human expertise from that perspective. So can the machine now do self-supervised learning to annotate, identify what those labels might be, and of course, through a process of validation, etc. So that was a framing of knowledge in our work. The other is, think about the teacher-student model, or that there's vast troves of knowledge that may exist out there with the teacher or with the books, and then the students take certain representations of this knowledge for the task or the work they have. Now we could apply this to large language models today. So let's say if there is a trillion parameter language model, whether it's GPT or Llama or what have you, that has been learned, can we build smaller LLMs from these different teachers from these very large language models, such that these smaller LLMs can be more task oriented and also can work in low resource, low compute environments, because sometimes because it's not possible to develop on everything on the web for, say, a university or folks in smaller companies, or even folks in countries which may not have access to such compute resources to do this work. So how do we take this large language model representation that exists, as assume that's a teacher, can we distill specific knowledge that we need to create smaller LLMs? So that is also knowledge centric, where we are trying to extract what we need as knowledge from already learned representation, and then trying to create specific smaller large language models to work on specific tasks. Finally, there could be a domain knowledge that comes to play. That domain knowledge is my expertise. So let's say if I'm interacting with the large language models, I may do prompt engineering, etc. Sometimes, and what we all have experienced, these language models have a tendency to hallucinate. Can I bring in external knowledge to revise, inform the performance of this? So what is external knowledge, right? The external knowledge could be things that I may have, I may create as a knowledge base or a knowledge graph from the World Wide Web, from the information of certain facts and etc. It could be my domain knowledge. It could be a chemist looking at some reactions and saying, no, I need to get this specific information out based on my interaction with this language model. Now, that is the domain, my expertise, the things that I have gleaned over a period of time in working with this. And then the question becomes is, how can this knowledge be used for real-world applications, etc.? So I'm going to walk through some of these frameworks, and the questions that we'll try to address is, as we think about distilling knowledge, what is it that we are trying to distill from this large knowledge framework? Are we distilling? Distilling is what piece of learned information that I may deem as knowledge in a larger model, if you will. Am I extracting the logics, the embedding layers, or the structures? Is it going from a teacher to student? Is it multiple teachers, single teacher, etc.? And how do we distill it? What kind of distillation mechanisms I may follow? So as you know, a lot of research that has been done is, folks have looked at how to distill different methods, what kind of structures, distillation schemes, is it online, offline, etc., that I may need from teacher to student. And most of our work has focused on really a one to multiple teachers plus using a graph neural network knowledge graphs and offline online mechanisms, and then as well as capturing the students are graph neural networks generally that we have considered. So one of the works that we did is what we call hypergraph masked autoencoders. This was recently published in AAAI, wherein what we're trying to say is that what if I can provide a masking strategy, and the knowledge that I would extract is, say, adjacency matrices that gets to the, which nodes are are next to each other. We could get node attributes as knowledge that may exist, and we could prescribe some meta paths to get some positional features or locations of the nodes. And then what if I give you a masking pattern? What if I say, hey, you mask the adjacency matrix, which is how the graph is, that's how the graph exists. And then can I learn those things based on other information? And so or can I mask the attributes and learn those based on the other information? So what that allows us to do is sort of develop confidence and allow the graph neural network here to optimize on, hey, based on the objective function that I'm going to learn to infer these based on this limited information, and I'll optimize on that. And then I'll get better, and I'll get better. So essentially, it's getting to that self-supervised learning framing where through this masking approach, we can make the graph neural network learn what is not known and then use that to infer labels on other things. And then what one can do is that once we have so this goes as part of the encoding layer, and then, we decode it using an MLP, and then as well as for the positional feature prediction, or just as a graph neural network. And those are the learning objectives that we set as part of this work. And then the other thing as well is that as we're thinking about teacher-student, like I talked about earlier, I'm sorry, if you have a teacher model, which is the large language model, let's say, which is representing a large graph neural network that exists, that is representing troves and rich knowledge, but I want to extract something very specific and then learn a smaller graph neural network on the very right. So how do I go about doing it? And then the knowledge is how similar the positioning that I talked about, the logits or the embeddings that exist in this teacher model, and how do I distill them down? So the other challenge, and why this is important for us to think about, if you look at this previous graph, is why is it important for us to think about the smaller student model? Is the computational, if I'm trying to learn a massive graph neural network on a massive graph structure, there is a significant dependence on the message passing architecture, which aggregates information from node neighborhoods. So more nodes means more computational dependency. So how do we sort of overcome this computational dependency framing such that our reliance on this message passing architecture is not as computationally extensive? And then if you look at GraphSage, which is the standard graph neural network learning algorithm, what GraphSage is doing is it grows exponentially. As we increase the number of layers to improve our performance, it increases the time complexity significantly from that perspective. And then that's where we are trying to sort of get to is, can we distill knowledge from a graph neural network to a multi-layer perceptron, which is very quick, which does not require message passing, as we all know. It's a very simple neural network architecture. And more importantly, the time of inference is small. So even if there is a large graph neural network that exists, and we can the cost of distilling it to an MLP for a specific task is insignificant. But the more important thing is, at the time of inference, the MLP is very efficient in terms of its performance. So that was also the idea, was that how do we take these massive graph neural network representation teachers and then in the end create a simple multi-layer perceptron student such that we have captured what we need about the properties or the attributes of that graph. And the perceptron has learned on that information and now is able to be used for any inferencing, etc. This is also very recent work that was in iClear last year. So finally, as we within this scope of the knowledge, the question for us is, we have interacted with large language models, or we have interacted with other data that may be represented in this graph neural networks as well. There are limitations to any of these struct, whether it's a graph or an LLM, etc. It knows what it knows based on the information that has been provided to it. Right? And then it's also doing, it's doing, generative AI, which is, stylistic or probabilistic stitching of sentences or words or pixels or sounds and things like that. And it does a remarkable job at that, no doubt. But then we have also experienced that these sometimes don't perform well. They may hallucinate, they may give you wrong answers. So could we leverage everything that these LLMs know, everything that's encoded as in these large graph neural networks, but improve the interaction through a knowledge graph or through an external knowledge base or domain knowledge? So I'll give you an example here. Let's say that we ask this question of ChatGPT, were there fossil fuels in the ground when humans evolved? Humans evolved 300,000 years ago, fossil fuels about 300 million years ago. And the correct answer is option C. And the answer that ChatGPT gave us at that time, and this was GPT 3.5, so we haven't checked it on the recent ones, is humans predate fossil formation. And it gives an explanation that does not make any sense. But not knowing, given the confidence it has in its explanation, etc., one may go, maybe this is a correct answer. So this is sort of a problem of hallucination where it is giving an answer and it is providing an explanation, and both are not correct. So what if I could provide a knowledge graph, which is a graph structure, and make sure that I can, and then this knowledge graph structure can serve as an input to guide the discovery of the answer in my interaction with, say, a large language model. So the way we have sort of worked on this domain is, so as a step one, we were given a knowledge graph or a general domain knowledge graph, etc. We do a subgraph retrieval and we extract subgraphs from this knowledge graph. And then we get an LLM dictionary wherein, what are the words, how they occur, blah, blah, blah. We get that and we convert that into a text embedding. So then now what we have developed is a graph neural prompting approach where these extracted subgraphs could be represented as a graph neural network in its encoding layer. And it could do node embeddings and what have you. And we can now do self-supervised link prediction as well to know, hey, these are the pathways in a knowledge graph that should be connected, etc. We could combine different modalities based on the LLM dictionary. And then this kind of a graph neural prompting learning that we have done now acts as a graph neural prompt along with the text embedding that was generated from the dictionary in its interaction with the large language models. So now we are giving a directional insight to within the embedding layers of a large language model to say, hey, the answer perhaps might be in this space. Use this knowledge as a starting point in your generative answer creation, responses, in your discovery of where to start within your massive 1 trillion parameter space. Because what happens is that it's a trillion parameter space, and depending on where we start and where we go, and then we probabilistically generate the next few words that come and sort of forces us along a directional search. So this is the work that is also recently published, where we are, again, incorporating external knowledge as a knowledge graph, building a graph neural prompt based on the learning, essentially embeddings, combining the LLM dictionary with it, and then together using it to inform a large language model. So just to cap up, so far what we've talked about is that if you think about, in the last 7-8 years, the pace this field has moved in learning on graphs, wherein heterogeneous learning on graphs with using different embeddings, different nodes, different features, etc., going down to how do we now capture their massive models, massive parameters. Cost of learning these is very expensive. Can we create scale-up approaches? Cost of annotations could be very expensive. Performance of these language models could not be correct. So can we leverage ideas of knowledge-centric, where can I infer labels, which is knowledge or annotations, through the machine learning model? Can I distill knowledge that I need to go from a larger model to a smaller model? And or can I provide domain knowledge in my interaction with these large language models? So that sort of has been a directional approach for a variety of research within the lab as well. But in terms of optimizing our frameworks of learning on these graphs. And recently, what we have also taken a significant foray into is what can AI do for chemistry or science from that perspective. So if you think about, one thing that to ask always is, hey, what is science? What does science mean? And according to the British Science Council definition, science is the pursuit of knowledge and understanding of the natural and social world, following a systematic methodology based on evidence. And then what is the definition of AI? This was from the book that I had used when I was a grad student, and it's still a book that's steadily used. And it's the study of intelligent agents that receive percepts from the environment and take action. It's implemented by a function that maps percepts to actions, and we cover different ways to represent these functions. There are productive production systems, reactive agents, logical planners, neural networks, or decision theoretic systems. Now, if you look at this definition of AI and we look at the definition of science, it is a big leap. Right? Science is talking about, am I understanding, am I discovering new knowledge, and based on evidence and following a systematic methodology, etc. And if you look at the definition of AI, it's more methodological based and perhaps evidence based on data, but how do we know it's actually leading to that discovery of knowledge, that we are creating new understanding of a natural or social world, what science wants us to do? So how do we bridge this gap between how we have considered AI mentally to go even beyond the world of prediction in many ways? What we're talking about here is, and it's not even interpretability or explainability. All of these things are components, but it actually is leading us to a new way of understanding of the natural world. And if we think about, enablement of different activities by AI, there could be exploration and discovery that we may do, community analysis and feedback that we may do, testing of ideas, benefits and outcomes. So how can AI, as part of the scientific discovery, where one is exploring and discovering, one is testing ideas, one is getting community analysis and feedback based on peer reviews, one is seeing what the benefits and outcomes might be, how can AI enable any one of these activities? And I forgot to include a citation to this figure, but this figure comes from University of California, Berkeley. I'm happy to share that link, and they actually have really nice framing of how this new way of scientific methods of discovery is done, again, from UC Berkeley. So what we have is we have an NSF-funded center at Notre Dame, what we call Center for Computer Assisted Synthesis. We are leading it at the university, and it involves several partners all across the country. And if I'm not mistaken, I believe Oles Isayev from CMU is speaking at this workshop, or speaking at some other event in Ukraine as well soon. So he's part of our network. He's a chemist, but he does very strong AI for chemistry as well. So this is a wide spectrum of expertise that represents, organic chemists, all the way from folks who are focused on synthesis, folks who are focused on reaction mechanisms, folks who are focused on who are doing both AI and chemistry, and folks who are doing more AI, machine learning, and less chemistry, and are trying to see how they can work with chemists to really enhance and solve these problems. So our vision of this center is simple. We want to transform how chemists discover, optimize, interrogate, and apply new reactions to the synthesis of functional molecules. And this vision speaks to the definition of science. There is knowledge discovery. There is new interrogation that will lead to new understanding. And we may create new functional molecules that I would be able to explain to you how these molecules are done. And we want to sort of go all the way, see how machine learning AI could be used for optimization, for mechanistic discoveries, for predicting what could be my reaction, for predicting what would be the yield of my reaction, and then eventually supporting synthesis. So that's what we're trying to do at the center. And some of the tasks that one may be interested in, that, hey, I could be interested in predicting toxicity of a property, which is a property of a molecule. I could be interested in synthesis, what kind of synthesis. I could be interested in yield, that even if I know these two molecules come together to generate an end product, it's not just knowing that I can create an end product. It also is, what is the yield of this end product? How much of that product have I created at the end? Now, one challenge that chemistry has is a vast number. It has imbalanced data problem, right? That vast the y-axis is the number of properties, x-axis is the labeling rate. A large number of properties don't have molecular properties labeled or annotated. Now, if I tell you, hey, you have to learn about property prediction, but you go, hey, but yeah, I don't have those labels available. And, it's not labeled because, it could be expensive to go through the wet lab experiments and things like that. And as a result, and if we look at the performance of a graph neural network, as the number of training nodes per class is low, they don't do as well in their property prediction. So how do we sort of overcome this gap of fewer properties that lead to poor performance can be increasing performance? So, but this is sort of, if you look at it this way, it is a few-shot learning problem wherein few properties have few labels attached to them, right? So what do we do from that perspective, that there's few properties that have few labels attached to them? And how do we now increase or enhance the mechanism of those properties, so to speak? So what we have done is we have said that even though few properties have labels, but there are many such properties in this database. So because there are many such properties in this database, and even if those few properties have labels, can we learn about those properties with each other? Because at the end of the day, they belong to a similar reaction class. So could we learn them collectively, do few-shot learning based on those labels that we have, and then improve the performance across the task? So we did a graph neural network where we can predict molecular properties. And then we sort of did the few-shot learning approach where we could ask an expert, we could have a query set, etc. And then we could build a complete framework. So I'll just quickly get you to the complete framework, how we are sort of working here. So each property we collect, as I said, there's 600 plus properties. We collect all their data. And then we have a support set that we learn a graph neural network on based on limited information that's available. We learn that, and then we have a query set where we say, hey, let's now give it a query set and see how that query, this is a typical few-shot learning approach where you have support and query framing. We give it a query set, the query set says, okay, thank you, I'm getting this, I will improve my performance, and I'll go on the cycle of support and query, etc. So that's what I'm going to do and build in terms of my few-shot learning approach. So I could have, from a molecular property prediction, what we show here is, this is our approach on the very end, that there's significant improvements in performance as compared to anything else that were possible using on this data for, say, toxicity prediction or the side of prediction, etc. So as we were going through this work, right, so we basically addressed the problem of few-shot learning, few labels, etc. The data that we have all been using is the data that's more readily publicly available. So then our question was, can we use these So ELNs are electronic lab notebooks. So our challenge was, could we now take everything that we know, the graph neural networks that we have developed, the few shot learning approaches that we have done, and leverage them to address the challenge of electronic labs notebooks, which is the sort of the North Star in reaction prediction, etc. That so the data that we all have used comes either through high throughput experimentation or is well nicely curated within databases. Electronic lab notebooks are not such well curated data sets. So could we get these electronic, and so we got, some 1,000 raw book Harvard reaction data points from AstraZeneca. And we said, okay, let's sort of now demonstrate that through amazing machine learning AI, we have tackled this problem. And so we got, in chemistry, there's a standard process called SMILES, which basically looks at the molecule and does a string-based structure, sequence-based structure on it. And then there are 3D structures that we have talked about, which is the representation of a graph. It does the DFT calculation, cheminformatics tools. And then we can combine all of this information to create a prediction model. So what we argued in our work is that what we've shown in our work rather is that one can connect sequence data with the graph structure of the molecule, and together they do much better because the graph structure of a molecule, when we learn of that, it can capture richness of the information, including orbitals, etc. So we created a graph neural network to address this challenge. And we were, we incorporated a variety of features: molecular volume, molecular weight, ovality, surface area, along with the node attributes that there may be in RDKML descriptors. So everything that was available that we could capture about these chemical reactions, we learned it, and we also had the singular, the feature vector, and the bottom layer is the sort of the sequential, the linear model, etc. that I was talking about. At the top is the graph neural network, and then we combine the two together to predict yield of a reaction. However, we were very disappointed with the results, right? So initially, when we started doing this work, our idea was that we would write an amazing paper that says, hey, we can take these amazing developments in AI right now, machine learning, using graph neural networks and everything else to tackle these electronic lab notebooks, which have sort of escaped a solution, which are a grand challenge problem if you ask folks in industry, etc. However, we did very poorly, and random forest that was not doing well on high throughput experimentation data, because the high throughput experimentation data is much larger, much bigger, so the graph neural networks could do much better. The ELGNN, which is a graph neural network method, these are R-squared values, did poorly. And the challenge was that the data quality is very poor in electronic lab notebooks, highly sparse, and we don't quite have a mechanism of really doing data set design from these sparse, low quality data. So that's a challenge for us, is how do we take these, how do we go from the 750 highly sparse, low quality data and be able to learn everything that we can to see what kind of yields will be more optimal. So instead of writing a paper on, hey, look how our method is doing, we wrote a paper that said, lessons learned, we are not ready yet, which was still a good exercise in many ways. So if you think about where would we like to go for, science and AI, there's this nice paper by Hiroki Kitano, which is on Nobel Turing Challenge, which talks about how do we create the engine for scientific discovery. And Nobel Turing Challenge basically saying is that, could we get to a place where AI is discovering through a very autonomous way, discovering the next scientific breakthrough? AI along with a human, but AI is an important partner to a human in doing that. Then we can say that AI has truly arrived for the world of science. But there's a lot more work that needs to get done, right? We are, today at a low task coverage and complexity zone. And we haven't quite achieved autonomy where AI is working autonomously, etc. AI is supporting the human more, augmenting the human more. There are assistants available, etc. But can AI be an autonomous partner to a human or to a process independently that leads to a scientific discovery? So if that's what happens, then it's a new scientific discovery for science, new knowledge, new understanding, new fundamental principles, but has also been used by AI. And it's called Nobel Turing because computer science doesn't have a Nobel Prize. Science does. Computer science has Turing Award. So could we create a Nobel Turing Challenge for computer science and science, the best of computer science and science is coming together to solve this. And with that, I thank you for your time, and I'm happy to take any questions in the last few minutes that we have.
Thank you very much, Nitesh, for amazing and very detailed and intensive work. I will need to rewatch some parts of it because it's very interesting. And yes, Alexander Isaev, indeed, he already gave a talk, and it's a funny coincidence and probably a good sign that we independently decided to contact you and him. So that means that, yeah, this direction that we are thinking about, it's indeed worth chasing. So yeah, now let's move to the questions. I'll share the screen in a second. The first question is, can you formalize, probably from the beginning of the talk, can you formalize what you mean by knowledge? How different is it from the usual labeled and labeled data? Sorry, you are muted.
Can we formalize what you mean? No, that's a very good question, right? It is labeled, unlabeled data. I mean, if you think about the way labeled data comes about, is right. There has been, and that's what we call supervised learning. There has been some supervision in creating labels. Unlabeled data, one could say, I'm going to simply use clustering, etc., because there's no Y available. I only have X, and if Y is available, it could be based on an observation of a system, based on the performance of a system, or based on a human input to a system. What we're saying is that there are several domains, as we've even seen in chemistry, wherein there would be a human is provided certain text, input, image, property, and the human says, this should be this should be this. And the human is using sort of a knowledge or an expertise to do that labeling annotation. What we are talking about here is in such domains where there is a human engagement required to create annotations, because the downstream tasks are about prediction, not about unsupervised learning, are about supervised learning. Can we, and if that labeling or annotation of a human represents the knowledge, could we do self-supervised learning to sort of create a representation? So that's what we mean by knowledge here. Things that may require domain expertise from a labeling perspective. Can we infer them directly using machine learning algorithms based on the patterns, trends we see? That is self-supervised. It could be any kinds of annotation, right? Then what is the second framing of knowledge that we have is, let's say there's a large teacher model that's available to you, but you can only afford to learn smaller student models for specific tasks. Can you extract what you need from the large teacher model, which is knowledge because it's already embedded, right? So now can you deduce what you need from there to feed to your smaller model?
Thank you. Next question is, if a system that is represented by a graph is dynamic, say authors start new collabs all the time, how reasonable is it to take the snapshots for learning?
That's also a very good question. Thank you for asking that. Any complex system is dynamic. That's a given. Any graph, any dynamic, any complex system is dynamic. So and that's where a lot of the work people focus on is link prediction. Will these two nodes develop a link in the future? Will these two nodes develop a new paper collaboration, etc.? So those are sort of our approaches to predict the dynamicism of a system. But there's also work that we have, what we do with machine learning is whatever data is available to date, we will use it and build a model. But then there's also work that we have done, which is focused on incremental learning, etc., that says, okay, as new information comes in, I will revise the internal mechanics of my graph structure. I didn't get a chance to get into that's a good question, get into the dynamics or how we are doing incremental learning or how we are leveraging the predictions or the predictive tasks are sort of addressing the dynamism of the graph, but those are very relevant.
Thank you. Another question is, are there any alternatives to graphs in terms of encoding complex systems?
So, I mean, yes, one could, if you think of it, a complex system doesn't come and say, I'm a graph, right? But a graph just allows us to capture interactions among components of a complex system. One could even say, oh, I'm just going to give you a sequence of things that happen, independent behaviors of these systems, then you put them all together. But graphs or networks allow us to capture the overall interactions among these components, how they interact, when they fire up, when they cool down, when they are relevant, when they form a link. Those things become what kind of attributes there may be, give us it's a data structure at the end of the day, a network or a graph. It's none of these are coming in and saying, hey, here is my graph, please use it. We extract that representation. So this just makes it easier to capture that interaction for us. Good question. Thank you.
Thank you. And maybe a few short questions from me. I know that we are over time, but it was like very interesting. And first, very short one about physics-informed neural networks. In a way, they are also graph networks, right? Because
yes.
Okay.
Yes.
And the performance when you add these basically additional like constraints by pumping the knowledge into the system, like creating this very difficult hierarchy and graphs, the performance, how much more performance you need to train such network in comparison to like more traditional approaches? Because at one slide you mentioned that multiple layered perceptrons, then you like win a lot, but still, like, can you say more details about it?
No, I think so. I wish I could. Well, I mean, that's a great question, and I know some folks who have been looking at how do we bring in more physics-based approaches and even more of a network science-based approaches that have originated largely from physics into the graph neural networks. I have not done work in this domain, so I don't have a good answer to your question, unfortunately, Vladimir. But it's a great question. I don't have a good answer to it.
Okay, and the very last one. On slide 39, let me stop sharing. On slide 39, maybe you can you share it again?
Slide 39. Yeah. Let me find Zoom, share.
Again, it's a bit out of the topic because it's more on the physical side of the things, but maybe you can give some extra details.
Slide 39. This one?
Yes, amazing. Yeah. This one. So this SMILES procedure, like these 3D structures, these are just data which is like raw data which already exists. Like, for example, you said this poorly notated like lab notes or something like that, or it's something that's the result of some pipeline where it's the sum of the data from crystallography databases, all sorts of other databases. So this chem informatics tools that includes also like already existing databases.
Yes, absolutely. So this is the databases that exist now with the AstraZeneca. So these are the mechanisms that exist. Right? One could use the databases, or one could use the SMILES process to create that sequence, etc. These mechanisms of generating this data already exist, or the data already exists. What we were trying to now see is, can we now bring it all together, as we talked about heterogeneous graph, and learn a yield graph neural network to predict yield.
Okay, I see. Thank you. Again, amazing talk. Thank you very much.
Thank you. Thank you so much for your time and your interest. Appreciate it. Good luck.
Thank you.